everyone. Thanks so much for being here. My name is Alena, this is Tara, and today we're going to be talking about GenAI model training on Kubernetes, specifically some of the considerations and takeaways around supporting distributed training at scale using open source tooling. So the first half of the session will be mostly informational. I'm going to talk a bit about the platform that we built at Capital One, as well as give an overview of distributed training with PyTorch, why it's needed, how it works, and how we support it on our platform. And then for the second half, Tara will be sharing our story of enabling job failure handling on the platform and some of the lessons that we learned from that process. So a little bit about us. We're both senior lead software engineers at Capital One working on the enterprise GenAI training platform. Our job is to support training, including pre-training and fine-tuning of large language models and other foundation models at scale. We've both been in the ops and/or ML space for close to a decade, and we started working on the GenAI platform around early 2023, which is right around when all the GenAI hype was starting up. So between the two of us, we've seen a lot of evolution of the tools and strategies used in this space over the years. So some context on why Capital One cares about GenAI. So Capital One applies AI and machine learning across a wide variety of core business domains, including, for example, fraud monitoring and detection, credit decisioning, et cetera. Within that, GenAI models are being trained and developed to power a growing set of both internal use cases, such as for agent servicing, as well as customer-facing products like AI assistants, as you can see in the screenshot. We also have a dedicated AI research organization that's advancing some cutting-edge techniques through training to evaluation and serving. So training and experimentation is a core part of how Capital One builds products, which means that it's pretty critical to the business to ensure that we have reliable, scalable, and up-to-date infrastructure and tooling for model development. So when building out a training platform to support large-scale distributed workloads, we chose to adopt as much open source as possible to stay close to the community, as well as to take advantage of the latest and greatest features that come out. So we use a mix of vendor-based open source as well as custom internal tooling. Our Kubernetes stack runs on AWS on EKS, and the core ML framework that we use is Kubeflow. So our customers use Kubeflow notebooks, pipelines for orchestration, Kserve for inference, and for distributed training, we use the Kubeflow training operator, specifically PyTorch-based training jobs. In terms of open source, we also use a lot of NVIDIA's tooling, like the device plugin for exposing GPUs, as well as DCGM exporter for telemetry. We also use Q for job scheduling and queuing on our more limited GPU resource types. In addition to that, we maintain custom operators and controllers for various GenAI and sort of general use cases, including, for example, GPU resource management, hardware fault tolerance, advanced scheduling, and things like that. So there are quite a few components that run on our clusters, and making sure all of these components are integrated and compatible with each other can be challenging, especially when adapting to new features or updates, which is part of the story that we want to share today. But before we get to that, I want to talk a little bit about distributed training, starting with why it's needed in the first place. So modern LLMs have billions of parameters and continue to get larger with every new release. For example, the largest current Llama model, 405B, has 405 billion parameters, which means it needs about twice that size in gigabytes to store the weights alone in 16-bit precision. And then in addition to that, during training, the GPUs need to store optimizer states, activations, and gradients, which can push memory requirements into multi-terabytes. So that simply does not fit on a single GPU or even on an 8-GPU machine. In addition to that, being able to scale out beyond a single node allows training work to be massively parallelized across hundreds or thousands of GPUs, which can greatly reduce training time from potentially months for large pre-training jobs down to weeks or even days. So the core training framework that we use is PyTorch. This is the library that provides the tensor computation engine and abstraction, and is responsible for the actual execution of the training of the model. PyTorch is an open source deep learning framework originally developed by Meta and is by far the most widely adopted library for both research and production workloads. A lot of popular GenAI frameworks are built for or on top of PyTorch today. So for example, the Hugging Face suite, NVIDIA's Megatron, Microsoft's DeepSpeed, the Flash Attention Library, etc. So PyTorch comes with a package called Torch Distributed that provides the core plumbing for multi-process, multi-node training. It provides high-level APIs for parallelization down to low-level primitives for communication. These include collective and peer-to-peer communication operations between processes, so in our case specifically GPUs. These collective operations are fundamental to how training work is able to be distributed out. At the lowest level, PyTorch abstracts over the communication backend to allow for different pluggable libraries for different use cases. So in our case, because we use NVIDIA GPUs, we use the Nickel backend, which is NVIDIA's collective communications library, which is specifically optimized for efficient interconnectivity between NVIDIA GPUs. On top of that, because we're on AWS, we also use a specific Nickel plugin developed by AWS that allows for optimized interconnectivity for AWS's proprietary interconnect hardware, which is called EFA. So there are three main types of parallelism involved in training. And in practice, if you're training across large models, you would use a combination of all three, which is known as 3D parallelism. So the most straightforward is data parallelism. This is where the model itself is not sharded, but the data is split up across the processes or GPUs. And during training, each GPU runs its forward and backward pass independently, calculates its gradients, and then those calculated gradients are synchronized across all of the GPUs. So this diagram is showing an example of PyTorch's distributed data parallel API. So you can see there are two processes or GPUs here, and the gradients are transmitted to each other in buckets using this collective communications operation called all-reduce. All-reduce is essentially sums up all of the gradients using this efficient algorithm, and then returns the average calculated to each of the processes so that by the end of the training step, all of the GPUs are in sync with each other. On the other hand, tensor parallelism and pipeline parallelism are both model sharding techniques. So these are used if the model cannot fit into memory. So for tensor parallelism, the individual weight matrices are sharded across the GPUs, whereas for pipeline parallelism, the layers of the model are split into different stages across the GPUs, which kind of creates an assembly line when training, where the data passes through each pipeline stage sequentially. Another core component of Torch Distributed is Torch Run, which is PyTorch's built-in launcher utility for distributing training jobs. And this specifically supports multi-process, multi-node training. It also has additional enhancements like support for elasticity and fault tolerance, which we will talk about in a minute. So when Torch Run is invoked, it launches one process per GPU on the local node and then coordinates with all of the other Torch Run agents on the other nodes to ensure that the job is fully up and running before training starts. So this initialization process is called rendezvous. Basically, all of the workers register with the rendezvous backend store to discover each other and establish a process group, which is an abstraction representing the set of distributed processes involved in the training and establishing how they are able to communicate with each other. We're going to talk a little bit more about rendezvous in detail with Tara in a second. So TorchRun provides the application level orchestration, but because we're running on Kubernetes, we need something that can actually bridge the gap between the application level launching and the actual compute resources that are needed to run the training job. So this is where the Kubeflow training operator comes in. It provides custom resource definitions for various distributed training frameworks. So not just PyTorch, but also TensorFlow, MPI, and others. So with the training operator, you can create a PyTorch job resource, specify the number of workers and other configurations, as well as the details of the TorchRun command that you are trying to execute. And then the training operator is responsible for the creation and management of the underlying pods. So making sure those pods are co-scheduled, that the statuses of the job are updated correctly, that the pods can communicate with each other through services, and are torn down appropriately at the end of training. In addition to that, the training operator also injects some key environment variables that are needed to allow TorchRun to run correctly. So for example, that includes the device, which is a unique ID for each machine or pod in this case, as well as the world size, which is an environment variable representing the total number of pods involved in the workload. So the combination of TorchRun and the training operator provides the core foundation for allowing distributed PyTorch training to run on Kubernetes. Yeah, so that concludes our crash course in distributed training. I'm going to pass it over to Tara now to talk about our case study in job failure handling.
All right, so distributed GPU jobs are actually pretty vulnerable to failure. This is because if any process in the process group fails, or the actual process running the process group fails, for any one of the instances, it will cause the entire job to fail. And they could fail for a variety of reasons. Think transient network errors, think bugs in the code. They could also fail for actual GPU failures. And this is not particularly uncommon. In fact, NVIDIA has a catalog of all the different types of GPU failures and what they mean so that users know. So because failure is inevitable here, there are standards for how to handle it. So first of all, so you have to really do two things. So the first thing is checkpointing. So think of checkpointing as saving your work. So when a job is running, it needs to be checkpointing, aka like saving the current state of things, how much it has done so far, so that if for some reason it has to restart and resume, it won't have to redo everything all over again. And you want to make wherever it's checkpointing to, like the actual storage, to be persistent. So think object storage, think persistent volumes in Kubernetes. So that's checkpointing, that's one piece of it. Then the second piece is the actual automated recovery. So like some process that will coordinate automated restarts when something fails. So there are a couple ways to handle, there's a couple that we're going to talk about. So the first way is actually using the PyTorch restart function. So this is like a native flag you can give to TorchRun. And so the way this works is you pass this flag saying to restart a certain amount of times, and if one of the instances fails for whatever reason, it will trigger a new rendezvous, coordinating with the rendezvous backend that Alena mentioned before. And then it will like cause all of the instances to restart. So all the TorchRun instances will restart their process groups. And notice this isn't a situation of the pods themselves that are running TorchRun restarting, it's the actual TorchRun restarting its process groups. And to go a little more into detail on this, we're gonna have to dig into the rendezvous backend situation. And so for the rendezvous backend, there's a couple different backends that you can configure. So the most popular one is C10D. And the way that works is it's actually launched with one of the TorchRun instances. So you'll see here, the one in the middle, that TorchRun actually like also pulls up the C10D backend that all of the other ones use to communicate and do the rendezvous. And so because we're at KCD right now, and so a lot of you work with Kubernetes, or I assume all of you do, you are all probably constantly tackling the problem of high availability. So I'm pretty sure all of you can kind of see the problem here in this architecture for restarts. And that's, what if that middle one there restarts? Well, luckily, we have other options for rendezvous backend. And our other option is configuring an etcd. So I know we all think of etcd as Kubernetes etcd, but etcd is also, it's a key value store, so it could be used for other things. And this is a little different than the C10D store where you tell PyTorch or TorchRun to use it and then it spins it up itself. This you have to provide it. It's a bring your own situation. And so you could deploy it on EC2s, you could deploy it on Kubernetes to be extra meta, you know. And then you basically have to point all of your TorchRun instances to use it. So this is kind of what it looks like here. It's like the one central one and all of them talking to it in the different pods. And this is really easy to configure with the training operator. So you could do this by defining the elastic policy in the training operator, or the PyTorch job spec. And you basically just need to tell the job where the actual etcd is. So just the IP address, the port, the DNS address, whatever. And it will propagate the environment variables to use that etcd as the rendezvous backend store to the pods it creates. So this is kind of what this looks like here. So as I was explaining before, you have the one etcd, you have the one over on the left is restarting, or had a failure, and all the other TorchRun agents are restarting their processes as a response. So they're re-rendezvousing, they're talking to the etcd store to coordinate that. So awesome, we love it. Okay, but upon tackling the problem this way, it became clear that the use of that configuration of restarts with etcd was not particularly popular, or at least we don't think it was, because we saw a couple of bugs in the open source. And of course, because we love contributing back to the open source, we contributed these fixes. So the first bug that we discovered was sometimes if we would launch a PyTorch job, it would just immediately fail if we set it to use etcd. And it turned out that that we were able to, when investigating it, figure out that whether or not it failed was dependent on which of the actual replica pods came up first. And from that, we were able to figure out that it was an actual race condition in PyTorch for handling the rendezvous with etcd. And we were able to put in a patch to them. So that was really cool, because they accepted that really fast. And then the other issue we found was with the training operator was that when we configure that elastic policy I talked about earlier, if it was misconfigured on a PyTorch job, it actually caused the entire training operator to crash. So that was pretty bad. So we fixed that as well, and they also, Qflow accepted that pull request. So we actually had an incredibly lovely experience contributing back. It exposed us to a lot of really talented developers. It helped us learn a lot about the tools we actually depend on, which is super important. And it gave us a feeling of like contributing to something larger than ourselves. And that was super cool. But still we wondered, why wasn't this etcd restart feature as supported as we thought it would be? Were we a bit too early in tackling the failure recovery problem? Was the open source ecosystem headed in a different direction? And so I feel like now is probably a good time to tell you all that this was actually in 2024. This whole story is 2 years ago. And that's important because we actually know the answer to this question. And that's the latter. The open source actually went in a different direction here to solve the same problem. And so in Trainer v2, which is the new version of the training operator that Qflow released last year, it actually depends on job sets in the back end. So job sets are a Kubernetes custom resource specifically for handling AI ML workloads. And one of the cool things they allow is they allow you like really granular control of how you want a job set to respond if one replica in the job set fails. So as such, in the trainer v2, you could define a train job and specify for if one of those replicas fails, bring all the pods down and bring them back up again, restart them all. So notice that this is done on the pod level, not on the torch run level that the previous implementation used. So this is actually a really good way of doing it, because it basically takes that responsibility off of PyTorch and puts it on the Kubernetes infrastructure, which is great. So what do we learn from this experience? So we learned that trying to solve a problem early means you, A, may be the first to find some bugs and regressions, and B, the community might end up going in a different direction than what you came up with. And as part of this, it's important to take note if a feature in the upstream is having frequent regressions. And honestly, if you're unsure of how the direction of how a project plans on solving a problem, it's a good idea to just talk to the maintainers. They're all lovely people, and honestly, we wish that we would have opened up this dialogue more in our experience with the maintainers instead of going right after this solution. And lastly, it's okay to choose a path that is less common or to consider pivoting later if another better path becomes available. Because as developers, deleting code and rewriting code is part of the job. Thank you.
We're open to Q&A if anyone has questions.
Hi. I was curious if there's still a use case for etcd, even with the newer, better solution that came out a few years after.
So I think the one advantage of using the etcd and using the torch run restarts is that you don't have to, so with the pod situation where it restarts the whole pod, if you had something that you had to do in the beginning of, before it goes to the checkpointing, so if there's like some kind of startup situation, you don't have to redo that if you're doing the torch run restarts, versus if the pod restarts, you have to restart the entire thing. So like if you needed to like preload stuff, whatever it was, like you have to do that on each pod again. Can you think of anything else, Alena?
I would also say like not specific to Kubernetes, but in general, like the etcd and other backends are still supported directly in native PyTorch. So if you were to use a non-Kubernetes-based framework where you didn't have access to the new trainer, it would still potentially be useful.